We are honored to have with us today Vida Dujmović. Vida is a professor at University of Ottawa and a research chair. Her research is focused around structural and algorithmic graph theory. On a more personal note, I was in a workshop that Vida organized as a graduate student, and it made a big impact on me. So it's nice to have her here. And now I'll be quiet and let's hear from Vida.
Thank you, Adam. Thank you for inviting me. I hope to be there in person the next time. So today I will tell you about completely new results, really, really new, so new that I finished these slides 20 minutes ago. So hopefully it's gonna go okay. So let me tell you about the results. And I was quite worried when Adam invited me. I was super happy. Yes, New York, maybe I'll even go in person. It didn't work out. I had, because of my exam, doesn't matter. But then after accepting, I got worried. I don't have any geometry results. What am I going to talk about? So this one has a little bit, it still is kind of my style. Typically, when I start with geometry problem, first thing I do is get rid of geometry. Okay, so let me start again with geometry. In fact, that's how we encounter this problem. And I would like this talk to be more kind of an advertisement of this, in my view, old problem that there hasn't been much advancement for 30 years. And it looks like we made some advance, but I think these problems are very interesting when it's on independent on geometry. But I'll tell you the story, though, in the way we bump into the problem. And that actually caused some of the issues, us knowing the correct background. We're only finding it out recently. But anyway, so here's a problem, a geometry problem that I have been interested for many years. And in the latest variation, it's stated like this. So if you think of a graph G being a planar triangulation, then a set of vertices in that graph is a collinear set if there is a straight line drawing of that graph where those vertices are on a line. Okay, so here's a picture. So this set of vertices, the green set of vertices, will be considered collinear set if there is a drawing, straight line, no crossings, and those green vertices are on a line. Okay, so that's a collinear set. And typically for our applications, we wanted this set to be as large as possible. But in general, here's another picture. These red vertices form a collinear set. So any set of vertices that you can put on a line and still have straight line drawings is a collinear set. So why would you care about these collinear sets? It turns out, although kind of it looks like they're restrictive, they're sitting on something very rigid, it turns out that these sets are super movable. Here's what I mean by that. If you have any, so we didn't know this for about 20 years, but we, as many groups of people, this goes back to many Barbados workshops. But here's what we found out is that if you have a set of vertices, if you have a drawing where a set of vertices is on a line, that set of vertices you can draw on any point set. It's completely movable. So you can do things like, for example, first of all, you can get it off of the line. That's an old trick, and you can move it such that such that y coordinate stays the same. But not just this, you literally can put it on any set. So you can change this set of vertices on the line. You can stretch these red vertices, put them in any way you like on a line. You still have a crossing-free drawing. Then you can extend them in the plane. In other words, if you have a collinear set of size S, and I give you any set of points in the plane, then there is a straight line drawing with those vertices, with a collinear set sitting on those vertices. And you can imagine that if you have some background in graph drawing, if you're interested in graph drawing problem, that this is super useful if you're trying to look at simultaneous embeddings, simultaneous crossing-free drawings, for example, where some subset of vertices sit on the same point set. The way we came about is from an old problem from beginning of 2000 about entangling graphs. I'm not going to go into it. At the end, I think this problem is super interesting on its own, which is what is the largest collinear set that every n-vertex planar graph has. And we can talk about triangulations. It's just, in this talk, I'll assume always the planar graph is the triangulation. So what we know today, sadly, is the same thing that we knew in 2007 when we solved this untangling problem. And in 2007, we didn't even know about collinear sets. But it turns out when you read that proof, it gives you a collinear set of size √10. So that is still the state of the art for collinear set. Linear is not possible. This was a result from 2007, but really it comes from these results about circumferences of three regular planar graphs, basically showing that their largest cycle in such graphs is something like n to the 0.98. So this gap is still there. So starting with geometry, at least I had an excuse to introduce you to this problem. Having so many geometers here, maybe finally somebody is going to break this bound. So √n is still the best bound for the largest collinear set in all planar graphs. Okay, but how would you find these collinear sets? Okay, and this is the point where you're already kind of moving away from geometry, but not really. We still stay with planar graphs of, let's say, topology. We're moving to kind of topology. So how would you look for such collinear sets? Somebody gives you a planar graph. How would you look for a collinear set? So years later after this, in other words, I think this was 2018, so 15 years after this untangling problem, we came up, I was visiting Fabrizio, so we learned that if you find a special kind of curve, let's say you start with a drawing embedding, not even straight line, drawing of a planar graph or planar triangulation in the plane, that if you find a certain type of curve, so you go with a pencil, in my case, it's this yellow pencil, and you start drawing a curve, and you manage to pick up lots of vertices, you are in good game, as long as this curve is meeting certain criteria. So we call this curve proper good curve. So what are the criteria? The criteria basically say that you can cross every edge at most once. So this is what this click here, you can cross every edge at most one, unless you containing the whole edge. That's allowed, right? You're not really crossing it. You can think of it that way. So if your curve goes through a vertex, like here, it's not allowed to go through a vertex again, or like there on the bottom, it's not allowed to go through an edge again, and so on. So in other words, endpoints are also considered part of the edge. So your curve is allowed to cross every edge at most once. And then if that curve manages to pick some vertices on its way, like in my drawing, then it turns out that those vertices form a collinear set. And we prove that this is if and only if. Okay, so if you have a proper good curve that picked up S vertices, then those S vertices form a collinear set. Okay, so that was what we proved in 2018. It allowed us to make some progress on these collinear sets of trees and max degree 3 planar graphs, but not the main problem. It also allowed Pat and I later on managed to make progress on bounded degree planar graph. So this is again the state of the art. If your graph has a bounded degree, so constant degree is basically linear. That was a year after that result. We managed to use these proper good curves and the circumference, many known results there about circumference of the dual. So we would start with a long cycle in the dual and trying to kind of pick up a vertex, right? But it turned out to be quite complicated. But anyways, the main thing still stands. So now we know that finding collinear set is the same as finding these proper good curves that pick up lots of vertices. So either one you like, if you find it, please think of, if you're interested, think about this problem about planar graph we are stuck at √10. My guess is that it's really bigger than √10, but that's the problem. We have been stuck on it since 2004, and as I said, we didn't even know that that's what we've stuck on. Now we learned that we are stuck on these proper good curves, but And we don't know how to solve that problem. So this was where we were at. And then we said, okay, this is too difficult for now. And then we decided to work with our students. Oh, by the way, I didn't say who the authors are. Pat Morin Jitbos, who is in the audience, and two of our students. We said, okay, especially in graph drawing, when you don't know how to solve something, you say, okay, what about if I allow a bend per edge? Okay, how big of a collinear set can I find? Okay, this doesn't sound like a super exciting problem, but somehow from this problem, we got to this connected dominating sets, which I actually find it's interesting problem. And I would think of this talk as an advertisement for this problem. And as I said, there's old history that we were discovering on the way. But it started with this one band collinear sets problem. So what is this problem? What is this version of the problem? So what you want is that, again, the same thing. I want to put as many vertices of my graph G, the given graph, on the line, but I'm allowed now when I'm drawing edges, they don't have to be straight. Each edge can have at most one bend. Okay, so for example, here in this drawing, all the vertices of G are on the line except for these two, but I'm using some bends, okay, on the edges. So when I want to know what is the largest collinear set if bends are allowed, where I'm only really interested in putting the vertices of the original. I don't care where the bends go, but I'm only counting vertices of the original graph. I want them to be on the line. Okay, you have seen that if you don't allow bends, that linear is not possible. Okay, but here, maybe even n is possible. Forget linear. Well, n is actually not possible, because if all the original vertices of the vertices of G are on the line, and you have allow only one bend, then no edge can cross this line. That means that each edge, otherwise it would have two bends, right? And so all the vertices are on the line, and if you only have allow one bend, then the edge is above the line or below the line. Well, that means that that graph is sub-Hamiltonian. You can add all the edges that are in between consecutive vertices on the line. And not all planar graphs are Hamiltonian. And then from Goldner-Harari graph, you get that you can put, if you take many copies of it, you get that you can put that even in one bend problem, the largest collinear set is at most 10 n over 11. So then, but it's still possible that it's n. Unlike planar graph, now we are going, okay, can we at least get n for this one bend drawing? So how will we do that? So remember, we learned this tool that you have this, all you have to do is find proper good curve. And if you find proper good curve, you can put all these vertices on the line. So forget about the bends. Let's look at this strategy. So again, the goal is, can we leave linear number of vertices? Do one bend drawings allow for linear collinear sets? Okay, so let's start with some strategy to find these proper good curves. And for now, pretend that no bends are allowed. Okay, so we are going back to the old problem. I want a long, proper good curve. So a curve that picks up lots of vertices and doesn't break my rules. Okay, so ignore the picture on the bottom. So let's look at the graph on the top, and let's say I find a spanning tree with lots of leaves. So we have this blue spanning tree here. And then I'm going to create my curve. Simply think of that standard holding your hand on the edge of a tree and walking around the tree curve. So you look at this thing here, that's the red curve, is simply the curve that you get by walking around the tree, okay? And it looks like, and then all the inner vertices, you imagine you make a little circle around them, right? I'm not picking up those vertices. So if you look at what's happening at the leaves, it looks like I picked the leaves, right? So if this is indeed proper good curve, if it's not breaking my rules, then my proper good curve is picking all the leaves. Okay, my collinear set would include all the leaves. Okay, but then, it would also work for planar graphs. So either in planar graphs, this strategy works, or this is not a proper good curve. Okay, so somehow we want, if this is working, we will want a spanning tree with lots of leaves, something that has been studied a lot as well. Okay, but let's see if this red curve that I drew, does it break a rule? So it breaks the rules all over the place. For example, look at these two leaves. They are endpoints of the same edge. So your red curve went to that edge and then touched that edge again. Over here as well, we have a curve picking that vertex. The other endpoint is crossed by the red curve. So here again, you look at an edge, it's crossed twice by the red curve. But, okay, so that is if you're not allowing bands. If you look at that strategy, you will fast realize that if you take every edge, the red curve crosses it at most twice, close to the vertex. Either it's picking a vertex or it's just close to it's walking around, so it's crossing it twice. So the red curve crosses each edge twice, close to the vertices. Well, that means that if I now take each of those original edges of a graph and subdivide these edges, those are going to be my bends. Now this curve is a proper good curve. Each edge is crossed at most once. Okay, so that means now I have this graph G, which is a subdivision of the original graph with at most one subdivision vertex per edge. And by the old theorem, that means that all of the leaves of the original graph, so those are the vertices of the original graph, can be on the line. Okay, so that brings us to the problem. Forget about the problem of this one band drawing. What is the largest? So here's a picture. What is the large? Here's a picture of a planar graph. This pink thing is a spanning tree, and the green vertices are leaves. So the question is clearly, how big of leaf set does every planar graph has? In other words, to state it better, over all spanning trees in planar graphs, which one has the most, how good of a bound can you get for the number of leaves? Okay, so you want to maximize the number of leaves. Okay, but before we do that, it turns out that finding a spanning tree with a maximum number of leaves is exactly the same problem as finding connected dominating set. Okay, so what does that mean? A connected dominating set is simply a dominating set that induces a connected graph. Okay, so let's look at why is that. So imagine you found, so this red, here I have this, these four red vertices. They dominate all the other vertices in the graph, and they induce a connected graph. Okay, and we have four vertices. They induce the connected graph. And now, if you look at all the remaining vertices are dominating by these vertices. So your tree can now be this connected dominating set, and all the other vertices are adjacent to that tree, to that connected. I mean, you have a connected graph induced by these four vertices. You can take a spanning tree of that. That's beginning of your spanning tree. Now all the other vertices are adjacent to this connected dominating set. So each one of them just picks one of them, say, you my parent. Okay, picks one red. So for example, in this case, so here's your connected dominating set, and this vertex here says, I pick this dominating vertex to be my parent, and you get a spanning tree where all the dominated vertices, not dominating, all the dominating vertices are now leaves in the spanning tree. So if you find the smallest connected dominating set, and then you found your maximum number of leaves in spanning tree. In fact, the sum of the two is n. Okay, so you start with a connected dominating set. You take a spanning tree of that. So you take the smallest one. You take a spanning tree of that connected dominating set. And that's the beginning of your tree. And then all the remaining vertices are dominated, but because they're dominated, they're adjacent to some vertex of the dominating set, and they pick it as a parent. That's your spanning tree. Okay, so looking for large connected dominating set is the same. Looking for a subtree with the maximum number of leaves is the same problem as looking for the connected dominating set. Okay, the dominating set that induces a connected graph. By the way, this was well known. Okay, so this one of the things I didn't expect that it's new, but you know, when you start looking more in the literature, seems to be super well known. There are books written about dominating sets, even chapters about connected dominating sets and so on. Okay, so that's why actually we set off to find the smallest connected dominating set. So that was our goal. All right, so to find so now you want to know what is the best known. What is the smallest connected dominating set in planar triangulations? Okay, so let's first of all start with dominating sets. Forget about connected. Okay, how small can it be? So I just realized that I didn't define dominating set. I hope everybody knows. So a dominating set of a graph is a set of vertices such that everybody who is not in that set has a neighbor in the dominating set. So in planar graphs, already in 1996, Tarjan and Matheson proved that there is a dominating set of size at most n/3. So that means that every planar, oh no, that doesn't mean anything about leaves because this is dominating sets, not connected dominating sets. And they also show the lower bound on n/4. So there's a gap of between 0.33 and 0.25. So that gap stood, I don't know if I can do this math, almost 30 years, no, 25 years. And 3 years ago, finally, the n/3 was broken. And there was first improvement was down to 0.32. And this year, basically, it's down to 0.28. So for classical dominating sets, we have a gap between n-quarter, and it's conjectured to be n-quarter and 0.28. Okay, what about these connected dominating sets? Okay, so this is the paper that we found originally. The paper is from 91, from Kleitman and West. So they showed that every planar graph has a connected dominating set of size 3n/5, so roughly 0.6n. But in fact, they proved it for something more general, for graphs that have a minimum degree at least 4, and each edge is adjacent to some triangle. Anyway, something that non-trivial planar triangulations meet. Okay, so we thought this is what we are trying to beat. We're going to try to beat 0.6. Okay, all in the back of our mind, I think there was always this n/2, beating n/2 sounded like a big goal. It's only recently, and by recently, I mean 2 days ago, that after some digging, we find out that actually there is a result from 1990 by Albertson, Berman, Hutchinson, and Thomason, who else, who proved that there is a connected dominating set of size at most n/2. In fact, that's probably why, because all along we were just talking about connected dominating set, Googling connected dominating set, even though we knew about this connection with leaves. But as soon as you start looking for maximum number of leaves in planar triangulation, you find this. There is their results, and it is expressed in the terms of maximum number of leads. So every planar triangulation has a connect dominated set of size at most n/2. Therefore, it has at least and spanning tree with at least n/2 leaves. Okay, so that was known in 1990. In fact, before finding that paper in 1990, I found this one here. It came from graph drawing community, where they prove in 2016 that every planar graph has induced outer plane. You want outer plane. They really wanted outer plane graph on at least n/2 vertices. Okay, this sounded like, what does this have to do maybe this problem? Outer planar is easy. You do breadth first search. You take your planar graph. You do breadth first search. You take every other layer. You get induced outer planar graph on n/2 vertices. But they really needed outer plane for their application. And they proved n/2. Okay. But if you think about, if you take connected dominating set, think of this connected dominating set and think of what happens when you remove it. And now you think of an embedding, think of an embedded planar graph. And there you have a connected subgraph. Imagine removing that connected subgraph. We know that everything that is left over, since it's dominated what I removed, it means that it has at least one edge into that face that removing this left. That means that the graph that is left in the plane is outer plane. Every vertex has a neighbor in the gap that I left. So yet another problem that is the same to this. Finding small connected dominating sets, what is left over is an induced outer plane graph. Okay, so their result was also known. I don't know if they know, but that's what I figured out 2 days ago. Okay, nevertheless, we thought we were beating 0.6, okay, but in fact, you really want to beat 0.2, and in the back of my mind, our mind sounded like that's an ultimate goal. And luckily, we managed to do that. So here's what the state of the art was for both problems. So this is dominating. The gap is now between 0.25 and 0.28, but that's not what we studied. What we really studied is connected dominating sets. The bound, conjectured bound is n/3, by the way. This is for connected dominating set. This picture here tells you why you need n/3. Okay, so you have to take, let's say from this triangle, you have to take some vertex, but because it's connected, you have to take a neighbor, at least one neighbor. Then to go in, you have to take at least one neighbor. So these nested triangles in the connected case give you n/3 lower bound. And n/2 upper bound stood until now, so 1990. All right, so what's the bound we proved? We proved 10/21, which is 0.47 for this connected dominating set. Okay, so let me give you an idea of how we did it. I'm not going to try to go in details. I'm going to try to give a big picture of how we do it. So the goal is to find connected dominating set. Okay, and we start with something kind of obvious. So we're going to do many tries. Okay, so let's, are there any questions at this point before I start explaining the approach? Okay, let's try to beat n/2. Or rather, let's try to beat 0.6, because that was kind of reasonably okay to beat. Okay, and then I'm gonna go to harder things, how we beat 0.2. n/2. Okay, so we start with obvious thing. I'm not going to flip to this page. Imagine you have embedded planar graph. The greedy thing to do is like, okay, I have to start something. I might as well start on the outer face. And you wanna, when you pick a vertex, say, okay, I'm gonna put you greedily in my dominating set. The greedy thing is to do is say, okay, pick the one that has the most neighbor, right? Pick the one that is going to dominate the most people. Okay, so here's that picture. So let's say this was our triangulation. I pick this vertex, it has the most neighbors, and I put it in my dominating set. Then I'm left, this becomes my new boundary of my graph, okay? All right. So boundaries, I always keep boundary dominated. So at the very beginning, I really have a triangle on the outside. I pick the vertex, like this one here, that was connected there. So I pick a vertex with the highest degree and put it in my dominating set. And then I get this new boundary of the graph. Boundary is dominated. In my pictures, boundary that is dominated will always be yellowish in color. And these guys that I put in dominated set, I'm going to try to draw them gray. And what's inside, not dominated, I'm going to try to keep it pink. Okay, so we pick the high degree vertex. We are left, this is new boundary. Boundary is dominated, but now I need to dominate these guys inside. So in what you really are trying to do when you're picking vertex greedily, you want to pick the vertex with the highest inner degree, in the outside, not on the boundary. Boundary is already dominated. Okay, so in this picture, for example, this vertex has 3 inner neighbor, 1 inner neighbor, 1. This one has 3. This one has 3. Okay, I might as well pick the one with 3 inner neighbors. Okay, so these are the 3 new vertices that now become part of the boundary and that are dominated, and so on. So that is a strategy. Okay, so let's see how far this strategy can take us. So let me repeat the strategy. The boundary is always dominated, and then I have to be picking somebody from the boundary because I also have to maintain that my dominating set is connected. I pick somebody from the boundary, then I pick next thing on the boundary, put it on the dominating set. So which one I'm going to pick? I'm going to pick, because the boundary is already dominated, I'm going to pick next to put in the dominating set, I'm going to put a vertex that has the most inner neighbors, most pink neighbors, because they're not dominated. Okay, so suppose that you can do that. So here's a try one, greedy strategy, try one. Suppose that you can always find a vertex whose inner degree is at least 2. Okay, so how good of a bound would that? And then you have to worry what happens if, is it even possible that you don't have inner neighbor of degree at most 2? I mean, you repeat this as long as you can. You keep on picking vertex of degree, inner degree 2, until you get stuck. Or maybe you don't get stuck, maybe you're lucky. So let's do that. And in fact, it turns out that you can get stuck. So remember I was picking, so this is what is left over. This is my boundary. You can think of this as, it can even disconnect the graph. These graphs are not so beautiful when you are picking them in some greedy fashion. Doesn't matter, but what I want to show here, remember these yellow vertices are your boundary. Now you want to pick one of these yellow vertices with the highest inner degree, with the most pink neighbors. But look, your graph looks like this. Each one of these has at most 1 neighbor. We are stuck. We cannot pick anymore a graph, a vertex with inner degree at least 2. So this is what we call one critical graphs. They actually really look like that. They look like outer planar graphs where in some, remember we are working with triangulations, we are eating it from the outside, so all the inner faces are triangles. So what we're left with, if you keep on eating vertices with inner degree 2, you are left with what we call a critical graph. It looks like this, and which is basically an outer planar graph where there are some triangles where you put 1 vertex inside. You have these K4s, and these pink vertices are not dominated yet. You have to pick somebody to dominate them. But this one, we're not going to do greedily anymore. We're going to solve it in an obvious way, right? Each one of them, you have to pick one vertex. Somebody has to pick this. So you can solve this, but each such K4s, you pick one of these yellow vertices, and you are done. Okay, so you repeat, remove vertices of degree 2, then we can show that once you're stuck, your graph really looks like this, and then you solve this graph. Okay, if you stuck. But first of all, imagine first, oh, this I didn't want to do on 2 slides. I want to do this on 3rd slide. But let's now do some counting. This is easy counting. I promise it's easy, because what we have in paper is not so easy. I'm trying to do this in an easy way. So imagine that you really can do this to the end. Ignore the bottom half. You ignore this thing that says with critical graph. Let's imagine that we are super lucky, that there is no critical graph, that we can go do this to the end. All of a sudden we look, what's left is, I don't know, just a path, orange path, everything is dominated, and we are done. There is nothing else. There's rather no pink vertices here, so that means we are done. Let's then figure out what is the size of this connected dominating set. Okay, so every time we pick, here's a little picture. So here's the gray vertex is the one that I put in dominating set. And then 2 of its inner neighbors that were not dominated now become part of the boundary. They are now orange. Okay. Okay. So next time, because I'm trying to make this connected, next time I pick a vertex with inner degree 2, let's say I pick this neighbor, but that one uncovers 2 inner vertices itself. Okay. Okay, I repeat my process. I am picking, okay, this is my boundary so far. One of them has degree 2 inner neighbors. I pick it, and then that one now has 2 inner neighbors. And imagine we can do this process, and at the end, the picture really looks like this. There is nothing left with dominated. Maybe this is just one outer planar graph here that we are dominating. So if we do the counting, we get, if X stands for the size of my dominating set, basically, the gray vertices that I was putting in the dominating set, every time I pick a new vertex to put a dominating set, maybe I killed one of the inner vertices, the one that were dominated already, but I also added 2 new inner vertices. So for each dominating set vertex, for each gray vertex, 1 orange vertex survived on the boundary that I didn't put in the dominating set. Okay, so the size of my graph in this rough counting, I have X gray vertices for each, just in a picture like there, for each gray vertex, 1 orange vertex survives. So the size of that is the size of my graph, 2x, should say here. And what is the size of dominating set? It's x. So this would give us n/2 proof. Okay, the one that we didn't know existed. But of course, this is completely incorrect, because we cannot always be lucky. I mean, it's correct if you're lucky, but you cannot always be lucky, because you can really end up in this situation. So when you are in this situation, you really do the only thing possible. You end up with critical graph, you complete your dominating set. You complete it by simply picking 1 neighbor of a pink vertex. Okay, so out of 3 neighbors, you pick 1. And by the way, we can show, even here, you can show, it's not so difficult to show, that there cannot be 2 of these pink triangle next to each other, because then this green, orange vertex, we'd have 2 inner neighbors. There would be 2 pink vertices in this triangle, therefore this orange vertex would have 2 inner neighbors, so we wouldn't have stopped. So that means that in this more general case, the size of the graph now is as before, but for each 3 vertices on the boundary, 3 orange vertices, we can have at most 1 pink unguarded vertex. So the size of our graph now is like this, plus the number of orange vertices divided by 3. So number of pink vertices is x over 3. So the size of the graph is 7x over 3. And the size of the dominating set, as before, we have x. And for each pink vertex, we had to pick one of its orange neighbors because otherwise it's not dominated. So therefore, the number of vertices we added is number of pink vertices, which is x over 3. So the dominating set has size 4x over 3. And the graph has size 7x over 3. So that's 4 over 7n. That's not less than n over half. We didn't make progress that easily, but it is less than n over 6. So we thought, okay, we beat that n over 6 result, which was never best bound to begin with. Okay, but at that point, okay, we have some result. All right. So, but really we wanted, even though we didn't know this, somehow n over half looked like a big goal. Okay, so we have to change the strategy because even, look at this, even if we can always pick a vertex with 2 inner neighbors, math tells us the best you're going to get is n over 2. N over 2 was known. We want to break n over 2. Okay, so you have to do better than picking a vertex with 2 inner neighbors. Okay, so you do obvious. Let's pick 3 inner neighbors. Okay, let's keep on greedily picking 3 inner neighbors as long as you can. Okay, let's try that strategy. Second try. So you repeat, you greedily pick. I have a boundary that is dominated, the orange vertices. I'm going to pick a vertex from the boundary that has 3 inner neighbors. Okay. Imagine you can come to the end of that. You're not stuck. All of a sudden, there's no vertex with 3 neighbors. Imagine you do that and you're super lucky. I just want to show you that if you could do that, you would prove the conjecture. You would get n over 3. If you really could pick always a vertex that has 3 inside neighbors. Okay. It's really the same picture as before. In this strategy, if you look at this picture on the top, when we were always getting 2 inner neighbors, as we are repeating the process, one of them survives. One of them doesn't become a part of dominating set. If we are able to pick 3, then the picture looks like this. Every time you pick a new vertex to put in the dominating set, maybe you killed one of the old ones, but 2 survive. Okay, so if you look, you can do this to the end until what remains is there's no more pink vertices. Then the size of your graph, here's your dominating set, has size x. For each vertex in dominating set, 2 of them survived on the boundary. Okay, that we didn't put in dominating set. So the size of the graph is 3x, size of your dominating set is x. So you found the dominating set of size n over 3. Okay, but we were stuck even when we were picking vertices with 2 neighbors, inner neighbors, let alone you really can end up with this graph. This is called, we call this one critical graph, where you end up with a graph where every vertex on the boundary has only 1 inner neighbor, 1 pink vertex. Okay. And we are here asking for 3, that all of them have 3. But again, if you're lucky, I mean, that is where the strategy is. If you're lucky, you get n over 3. Okay. All right, so we cannot get 3. It's very easy to come up with examples where you cannot get 3. So when we cannot get 3, we first think, okay, let's fall back to the one where you can get 2, because when we were removing 2, at least we got that graph that we really understand, that one critical graph. Okay, so our strategy now becomes, you want to pick 3, you pick 3, and all of a sudden you don't have a 3. Okay, then you're going to say, the only reason not to pick a 3 is because you don't have it, right? That is obvious. Okay, so now you say, do I have a 2? Okay, so what we're going to show is that And I'm not going to explain it, but the strategy is going to become when you don't have a 3, you pick a 2. And then most of the time, so like in this picture, look at this picture here. If this is your boundary, if this is your orange outside, every vertex on the boundary has only 2 inner neighbors. That's that situation. So what we showed is that for a long time, let's say it like that, for a long time, you can pick, if you are forced to pick a vertex of the degree 2, like here, once you remove it, you, of course, new vertices appear on the boundary. One of its neighbors has inner degree 3. Okay, so one of the new vertices that appeared on the boundary has a degree 3. Okay, so the strategy now, greedily, we do this, we alternate. You start, you don't have a 3, you pick a 2, and then its neighbor has a 3, then a 2. So you keep on doing this, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, until you get stuck. Okay, so now what you get stuck with is different. But before even going there, imagine again, what if you're lucky with this strategy? What bound would you get? You are picking 2, 3, 2. We saw that if you can always pick 3, 2, 3, 3, you get optimal bound. You get n over 3. Not only you beat n over 2, you get optimal bound n over 3. Okay. What happens with this strategy? 2, 3, 2, 3, 2, 3, and you are lucky, you are done when you run out of possibilities. Do you beat n over 2 then? Well, that same counting type thing, I'm not going to bother you with that. Then remember strategies, you pick a vertex of degree 2, 1 survives, then you pick vertex of degree 3, 2 survive, then you pick vertex of degree 2, 1 survive. You end up with something like this, and nothing is left over. This is that hypothetical situation that you are done. Then your X is, if this is your X again, your dominating set, now what survives is basically 1.5x, and your dominating set is X. So when you plug this in, you get 2/5 n. So that's less than a half. Okay, so in this case, you get something less than a half with this super wishful thinking that nothing is left over when you get stuck. Okay, so here's what you get when you are stuck. All right. So to make this work, first of all, you repeat this strategy. How much time do I have left? I'm not going to go into details. What is the typical length of the talk?
Or so, I guess 9 minutes is the standard, but flexible.
No, I don't need to go above. I don't
Okay.
need to go above. Sometimes it's 50 minutes. That's why I'm asking.
Up to you. In case it matters, there are a few messages in the chat. I don't know if you want to look at them.
No,
now.
I'm not gonna. I don't plan to stay longer. I mean, I'm finishing up because now it becomes a little bit hairy. Okay, so let me say what we're doing. So we keep on doing this to remove 2, remove 3, remove 2, remove 3. Then in this alternating reading process, you're going to be creating also not things that are nicely too connected. They will be kind of, think of removing stuff for planar graph. You're going to end up with trees, and that mess also starts causing lots of problems. So in this process, we're also doing sort of cleanup, arguing why you can do it. Doesn't matter. So when this alternating process stops, you end up with this graph, a graph that we call two critical graph. Look, so these blue vertices are what were usually yellow vertices. So this is our boundary vertices. Look at this. So what we were saying, if you don't have a 3, everybody's a 2, you're gonna pick a 2. Okay, so this one has 2 inner neighbors, 2 inner neighbors. Everybody on the boundary has 2 inner neighbors. So it looks like I'm in one of those situations where I should pick a 2 and then pick a 3. But actually, these two critical graphs, if you pick a 2, there is no more pick a 3 inside. Okay, and then we show that the structure of the graph is exactly like this, at least the two connected ones. So basically, it's a graph that is, you can think of it as graph that has 2 layers. Okay, so outer planarity 2, so it has those vertices. Everybody has two neighbors. Inside, you have that one critical graph, the old one, where everybody has one neighbor. Okay, so, and now we have to solve the problem on just this class of graph. I mean, this is where we spend a lot of time solving. So you're doing this greedy thing, and then you and clean up of things hanging until you end up with two connected graphs that look like that. Everybody on the outside has 2 degrees in. When you remove all of outside, inside is that all one critical graph that we have seen, this one critical graph. So that is what a graph looks like. And when you wanna, so we need to color that graph efficiently. And it turns out that even that was really the obvious thing we're all breaking. So I'm not gonna go into that. But that's the algorithm. Okay, but at least this kind of graph, it has 2 layers, 2 outer layers, and when you remove them, you have isolated vertices, you know, so it's kind of a graph that we can handle in a better way. In fact, we somehow find this is a graph for which we can do optimal n/3 solution. Okay, so that's the result. I even put the counting here, but I'm not gonna do that. I want to end with summarizing the open problems. So first of all, the one that is not about, well, I guess it is about graph theory and about geometry. What is the largest collinear set of planar graphs? And now we know that that's the same as asking what is the longest proper good curve, or what is the proper good curve with the most vertices in any planar graph. The best we know is root n, and we know that it's not all of n. We know it's not linear. Smallest standard dominating set, we didn't study that, but somehow it fits here. So the smallest standard dominating set, the gap is narrowing. Conjecture is one that a quarter is correct for the smallest dominating set. Smallest connected dominating set, conjecture is n/3, but at least we are now broke n/2 bound. Remember the connection with largest leaves, number of leaves in a spanning tree. That means that what's left over here, so basically we have a spanning tree with more than half leaves. Because we have a connected dominating set of 10/21, the rest are the leaves of that spanning tree. So we have every planar graph has a spanning tree with at least, or rather, not every planar. I keep on saying planar graph, but the path doesn't. It has only 2 leaves. Every planar triangulation, the whole talk is about triangulation. I hope I didn't introduce a problem with that. If your planar graph is a path, obviously every spanning tree has at most 2 leaves. Triangulation. So every triangulation has a spanning tree with at least 11/21, so more than half vertices. Conjecture is n/2 n/3, basically matching this n/3 for the connected dominating set. Again, on the fly, I explained this connection that if you have a connected dominating set is the same as the largest induced outer plane graph. So what's left over, the graph induced from that is outer plane. And now we know that we have induced every embedded planar triangulation has induced outer plane graph with more than half of the vertices, which brings me to this problem that maybe some of you know that I couldn't find anything about. I mean, it looks like that even forget about embedding, what is the largest induced outer planar graph in every planar? Now you don't even need triangulation in every planar graph. So if you just do, as I mentioned, if you just do breadth first search, you get n/2. Trivially, you take the every other layer, you take the bigger of the 2. I couldn't find anything. And it looks like that then we even beat that's triviality. And you know, it sounds like something like this should be known. But I couldn't find it. There is a famous problem. I'm going to end with that. There is a famous problem that asks something similar, which is what is the largest in every planar, I think it's also triangulation, what is the largest induced graph, what is the largest induced forest? I'm asking what is the largest induced outer planar graph? Trivially, it's n/2. It's a well-known open problem, apparently, after all this searching that I did. It's a well-known open problem. What is the largest induced, open for decades, what is the largest induced forest in every planar graph? N/2 is conjectured. And they're, going to that bound. That n/2 is conjectured. But for outer-planar graph, I don't know. Well, now it's less than a half, because outer plane is less than a half. But maybe outer planar is known. Okay, that's it. Thank you.
Thank you very much.